High above us, invisible rivers of water drift in silence, shaping the mood of the world below. They gather without sound, dissolve without farewell, and travel enormous distances while carrying nothing heavier than breath. Tonight, as you settle into stillness, we will drift upward together, past rooftops and treetops, into the soft architecture of the sky. We will learn how clouds form, how they move, and why these delicate structures have held human attention for thousands of years. There is nothing to do now. Only listen and let the sky rearrange itself slowly above your resting mind. Welcome to Let's Learn While You Sleep. Tonight, we turn our attention upward to the quiet architects of the sky, the clouds. They are the most familiar strangers in our lives, drifting overhead every day, and yet most of us have never truly studied them. Clouds are not solid objects, though they appear so. They are immense, shifting gatherings of water droplets and ice crystals, each one smaller than a grain of pollen, suspended in the currents of our thin blue atmosphere. Some weigh more than a fleet of airliners, and still they float. Some stretch for hundreds of kilometers, and still they vanish in hours. Over the next hour or so, we will explore how these structures are born, how scientists learn to name them, and how they shape the weather, the climate, and even the way light reaches the ground. There is no need to remember anything. Let each idea pass like a cloud itself, softly overhead, as sleep begins its slow approach. To understand a cloud, we must first understand the air around it. The atmosphere of Earth is a thin, restless ocean of gases, mostly nitrogen and oxygen, with traces of argon, carbon dioxide, and a small but crucial amount of water vapor. This vapor is invisible. It rises from oceans, lakes, soil, forests, and even from your own breath, lifted upward by the warmth of the sun. For every cubic meter of air near the surface, there may be only a few grams of water dissolved within it, and yet this tiny amount holds extraordinary power. When that air rises, it cools, and when it cools, it can hold less vapor. At a certain point, called the dew point, the vapor has no choice but to change. It condenses, gathering onto microscopic particles already drifting in the sky, specks of dust, grains of sea salt, fragments of pollen, tiny flakes of soot. These particles are known as cloud condensation nuclei, and without them, clouds as we know them would struggle to form at all. Each droplet that appears is astonishingly small, roughly 20 micrometers across, far smaller than a human hair is thick. Billions upon billions of these droplets together form what we see from the ground as a single soft shape drifting across the sky. And so a cloud, in the most literal sense, is simply a vast cooperative of water made visible. A gathering made possible only because the air itself grew cold enough to let go of what it had been carrying. Consider for a moment how much invisible movement surrounds you right now. The breath you just released contained water that will, in time, rise, cool, gather onto a speck of dust, and perhaps join a cloud somewhere far from here. The sky is not distant. It is continuous with the room you rest in, and with every slow inhalation, you are quietly exchanging atoms with it. For most of human history, clouds were described in the language of poetry rather than science. They were omens, moods, messengers, the breath of gods, or the thoughts of the sky. It was not until the early 19th century that a young English pharmacist named Luke Howard proposed the system of naming we still use today. In 1802, Howard presented a lecture in London in which he suggested that clouds, though endlessly varied, fell into a small number of basic forms. He borrowed from Latin, the language of scholars, to give them names that could cross borders. He called the thin, feathery clouds cirrus, meaning a curl of hair. He called the heaped, rounded clouds cumulus, meaning a pile or a heap. He called the flat, layered clouds stratus, meaning a sheet or a spread. And for clouds that carried rain, he added the word nimbus, meaning a dark mist. These four root words, in combination, could describe nearly any cloud in the sky. A nimbus stratus was a rain-bearing sheet. A cumulonimbus was a towering heap of storm. A cirrostratus was a thin, high veil. Howard's insight was quiet but profound. He gave the sky a grammar. His system was taken up with enthusiasm by scientists and artists alike. The German poet Goethe wrote verses in Howard's honor. The English painter John Constable studied clouds with new precision, sometimes dating his sketches with the hour and the wind direction. And slowly, across the 19th century, meteorology began to emerge as a true science, grounded in careful observation of what had once seemed too changeable to study. Today, the World Meteorological Organization recognizes 10 main cloud genera, subdivided into species and varieties, much as biologists classify living things. And yet, at its heart, the system still rests on Howard's original 4 words, spoken softly in a London hall more than 2 centuries ago, on an evening when he simply suggested that even the drifting sky might be understood. Let us drift now through the layers of the sky and meet these cloud families where they live. The atmosphere, though it seems continuous, is arranged in invisible floors. The lowest layer, the troposphere, begins at the ground and rises to about 12 kilometers above the surface, though it is thinner near the poles and thicker near the equator. Nearly all weather and nearly all clouds occur within this single layer. Within the troposphere, meteorologists recognize 3 broad heights at which clouds tend to gather. The low clouds, below about 2 kilometers, include the soft grey sheets of stratus, the lumpy rolls of stratocumulus, and the dark, rain-heavy nimbostratus. These are the clouds that often sit close enough to brush against hillsides, the clouds that dim the afternoon and soften every shadow. The middle clouds, between roughly 2 and 7 kilometers, carry the prefix alto, from the Latin for high. Altostratus spreads as a pale, translucent blanket through which the sun appears as a watery disk. Altocumulus arranges itself in patterned patches, sometimes called a mackerel sky, resembling the scales of a fish. The high clouds, above about 7 kilometers, are thin, cold, and made almost entirely of ice crystals rather than liquid droplets. Here live the cirrus, drawn out into delicate filaments by fast upper winds, along with cirrostratus, which can veil the entire sky in a pale whitish haze, and cirrocumulus, which dots the high blue in small rippled clusters. Above all of these, in rare cases, rise the great towers of cumulonimbus, which may stretch from near the ground to the very top of the troposphere, more than 12 kilometers tall, anvil-headed and cathedral-like. Each layer has its own temperature, its own winds, its own rhythm. The sky, seen this way, is not a single ceiling, but a series of quiet rooms, each with its own residence, each with its own light. And tonight, as your thoughts settle, you can imagine yourself moving slowly through them, from the warm low mists to the icy ribbons far above. Of all the cloud families, cumulus may be the most familiar, the cloud a child draws without thinking. It rises in soft heaps against a summer sky, its top rounded and bright, its base flat and grey. That flat base is not decoration. It marks a precise boundary, the altitude at which rising warm air has cooled just enough for its vapor to begin condensing. Every cumulus cloud in the same region tends to share almost exactly the same base height, because they are all born from the same cooling threshold in the same body of air. Watch them long enough on a calm afternoon, and you can see the process itself. The sun warms patches of ground unevenly, a dark field, a paved road, a stretch of rock, and the air above these patches grows lighter and begins to rise. This rising column is called a thermal. As it lifts, it cools at a remarkably steady rate, roughly 10 degrees Celsius for every kilometer of ascent, while it remains dry. When it reaches its dew point, condensation begins, and a small cloud appears almost out of nothing, as if the sky had taken a quiet breath. If conditions are gentle, the cumulus will remain small and scattered, drifting politely across the afternoon. These are the fair weather cumulus, the signature of stable, untroubled days. But if the atmosphere above is unstable, and the rising air continues to be warmer than its surroundings, the cloud can grow. It swells upward, building story upon story, its top hardening into bright cauliflower shapes. Given enough energy and moisture, it may eventually become a cumulonimbus, capable of producing thunder, lightning, hail, and torrential rain. And yet, even the mildest cumulus is a performance. Each one is a visible record of warm air rising, of invisible water changing form, of the sun's energy being quietly redistributed through the atmosphere. The sky above a summer field is never still. It is simply busy in a way we cannot usually see. Above the cumulus, in the middle layer of the troposphere, we encounter altocumulus and altostratus, clouds that live between roughly 2 and 7 kilometers above the ground. Altocumulus often appears as small, rounded masses, arranged in groups or waves, sometimes described as a mackerel sky. because the patterning resembles the scales of a fish. These clouds form when gentle pockets of warmer air rise through a layer of cooler, more stable atmosphere, each pocket condensing into a soft, individual tuft. Altostratus, by contrast, spreads itself thin, forming a uniform grey or blue-grey veil that often covers the entire sky, dimming the sun until it looks like a pale lamp shining through frosted glass. This veil frequently signals the slow approach of a warm front, where a broad mass of warmer air is sliding gently up and over cooler air beneath, lifting and cooling as it climbs, condensing across hundreds of kilometers. The beauty of these middle clouds is their role as quiet messengers, hinting at weather yet to come, often hours or days before it arrives. Sailors, farmers, and pilots have read them for centuries, learning to translate their textures into forecasts. A sky that shifts from cirrus to altostratus to nimbostratus is in many regions the unmistakable signature of incoming rain. And yet the clouds themselves do not hurry. They drift with the patience of continents, obeying winds whose speeds they neither question nor resist. Consider for a moment how remarkable it is that water, in its lightest possible form, can organize itself into such distinct architectural styles, depending only on the temperature, pressure, and motion of the air it inhabits. The same molecule, the same simple arrangement of 2 hydrogens and 1 oxygen, becomes a feathery cirrus thread at one altitude and a flat altostratus blanket at another. The atmosphere, in this sense, is a vast sculptor, and the clouds are its endlessly changing galleries. Somewhere above you now, even if the night sky looks clear, these middle layers may be quietly forming, reshaping, dissolving, performing their slow choreography in the dark. Higher still, in the coldest reaches of the troposphere, we find the cirrus family, clouds composed almost entirely of ice crystals rather than liquid droplets. At altitudes between roughly 6 and 13 kilometers, the temperature is so low, often below -40 degrees Celsius, that water vapor bypasses the liquid stage entirely and crystallizes directly into delicate hexagonal ice. Cirrus clouds appear as thin, wispy streaks, sometimes called mare's tails, drawn across the sky by high-altitude winds that can move at speeds of over 100 kilometers per hour. These winds stretch the ice crystals into long, feathered filaments, and because the crystals fall slowly as they drift, the cirrus takes on that characteristic curved, trailing shape, as if the sky itself were being brushed by an invisible hand. Cirrus clouds are not rain clouds. The ice within them rarely reaches the ground, usually sublimating back into vapor long before it descends through the warmer air below. And yet cirrus plays a subtle and important role in the planet's climate. Because ice crystals are excellent at trapping infrared radiation rising from the Earth's surface, a sky filled with cirrus tends to warm the surface slightly at night, acting like a thin, high blanket. During the day, the same clouds reflect a portion of incoming sunlight back into space, producing a small cooling effect. The balance between these two effects is one of the ongoing areas of study in modern atmospheric science, and researchers are still refining their understanding of how cirrus coverage responds to and influences global climate patterns. There are also closely related forms, such as cirrostratus, a milky veil of ice crystals that can cover the entire sky and often produces halos around the sun or moon, and cirrocumulus, small rippled patches of ice that resemble grains of salt scattered across dark velvet. All of these high clouds share a cold, luminous quality, shimmering faintly in the thin atmosphere far above the weather we feel, reminders that the sky has floors and ceilings and countless quiet rooms we never visit. There is one cloud that deserves its own quiet chapter, for it is the giant among clouds, the architect of thunder and lightning, of hail and sudden downpour. This is the cumulonimbus, a towering vertical structure that can rise from just a few hundred meters above the ground all the way to the top of the troposphere, sometimes reaching heights of 12 or even 18 kilometers. To put that into perspective, a fully developed cumulonimbus can be taller than Mount Everest and may contain more energy than a small nuclear weapon, though that energy is released gradually in the form of rain, wind, and electrical discharge, rather than in a single catastrophic moment. The cumulonimbus is born when warm, moist air rises rapidly through an unstable atmosphere, condensing as it climbs, releasing latent heat that fuels further ascent. This self-reinforcing process, known as convection, can continue for hours, building the cloud into a vast anvil-shaped mountain of water and ice. The flattened top occurs when the rising air reaches the tropopause, the boundary where the stable stratosphere begins, and can climb no further. Instead, it spreads outward, forming the characteristic anvil shape that can be recognized from hundreds of kilometers away. Inside the cloud, powerful updrafts and downdrafts churn water droplets and ice crystals against each other, generating enormous electrical charges. When the difference in charge between different parts of the cloud, or between cloud and ground, becomes large enough, it discharges in a bolt of lightning, a plasma channel that briefly heats the surrounding air to around 30,000 Kelvin, roughly 5 times hotter than the surface of the sun. The sudden expansion of that superheated air is what we hear as thunder. And yet, for all its drama, the cumulonimbus is simply water and air, obeying the same laws that shape the gentlest cumulus. It is the scale, the energy, the patience of accumulation that transforms a fair weather puff into a storm. Somewhere on Earth, right now, hundreds of these towers are rising quietly into the sky, and hundreds more are dissolving back into stillness. Now, let us drift to the lowest rooms of the sky, where clouds come so close to the ground that they sometimes touch it. Stratus clouds are the flat, featureless grey layers that often hang low over landscapes in the early morning, softening every edge, muting every colour, turning the world into a quiet watercolour. They form when a large, stable mass of moist air cools uniformly, either by gentle lifting or by contact with a cold surface, and the water vapour condenses into a broad, thin sheet of tiny droplets. Stratus clouds rarely produce heavy rain, but they can release a fine drizzle, or simply coat every surface in delicate mist. When a stratus cloud forms at ground level, we give it a different name, one of the oldest and most poetic words in meteorology: fog. Fog is, quite literally, a cloud that has come down to visit, and walking through fog is walking through the inside of a cloud. A closely related form, nimbostratus, is the thicker, darker sibling of stratus, a deep grey layer that produces the steady, hours-long rainfall often associated with slow-moving warm fronts. Nimbostratus lacks the drama of cumulonimbus, the sharp edges of cumulus, the delicate feathering of cirrus. It is instead patient and persistent, a cloud of quiet endurance that soaks the earth gently and deeply. And then there is stratocumulus, a kind of middle ground between stratus and cumulus, a low layer broken into patches and rolls, often covering the sky in soft, lumpy geometry. Stratocumulus is, by some measures, the most common cloud type on Earth, covering roughly a fifth of the planet's ocean surface at any given moment, reflecting sunlight back into space and quietly cooling the climate. So even as you rest here, these low, humble clouds are performing their steady work, shaping temperature, shaping light, shaping the air we breathe. From the highest cirrus to the lowest fog, the sky is always full, always moving, always writing and rewriting itself in vapor and ice, a patient architecture we rarely pause long enough to read. And now, as our journey through the sky's quiet rooms continues, let us pause to consider how clouds are born in the first place, for the process is so unhurried, so patient, that it feels almost like a kind of thinking. A cloud begins with something we cannot see, water vapor, invisible and weightless, rising from oceans and lakes, from forests and soil, from the breath of every living thing. This vapor drifts upward on currents of warm air, and as it climbs, the atmosphere around it grows thinner and colder, and the vapor begins to slow, to cool, to seek stillness. And yet, vapor alone cannot become a cloud. It needs a partner, a tiny companion called a cloud condensation nucleus, a speck of dust, a grain of sea salt, a fragment of pollen, a trace of volcanic ash, sometimes even a single molecule drifting up from a distant forest fire. Around this minuscule anchor, water vapor gathers, condensing into a droplet so small that millions of them could rest upon your fingertip without weight. Scientists estimate that a single cubic meter of cloud can contain hundreds of millions of these droplets, each one holding its partner particle at its heart. Consider for a moment the strangeness of this. Every cloud you have ever seen, every towering thunderhead, every delicate wisp of cirrus, every blanket of morning fog, is a vast cooperative gathering of water and dust. Two things that seem so humble on their own, yet together compose the shifting architecture of the sky. And the particles themselves travel astonishing distances before finding their droplet. Saharan dust has been measured drifting across the Atlantic, seeding clouds over the Amazon rainforest. Sea salt from crashing waves rises invisibly into the upper atmosphere, becoming the quiet seed for storms thousands of miles inland. In this way, the clouds above you may carry within them the memory of deserts you have never walked, oceans you have never crossed, forests whose names you do not know. The sky, it seems, is always remembering the earth. Let us drift now into the strange and almost secret realm of clouds that form far above the ones we usually notice. Clouds so high, so rare, that for most of human history, no one knew they existed at all. Somewhere between 76 and 85 kilometers above the Earth's surface, at the very edge of the mesosphere, there exist clouds called Noctilucent clouds, meaning, in Latin, night shining. They are the highest clouds in our atmosphere, forming in a region so cold and so thin that it was long believed no cloud could survive there. And yet, in the summer months at high latitudes, when the sun has set below the horizon but still illuminates these impossibly distant wisps from below, they glow with an eerie electric blue light, shimmering like silver threads across the twilight sky. Noctilucent clouds were first reliably recorded in 1885, 2 years after the catastrophic eruption of Krakatoa, and some scientists wonder whether that eruption, or the rise of industrial activity, may have contributed to their appearance. Current evidence suggests these clouds form around meteoric dust, the remains of tiny meteors that burned up in the upper atmosphere, leaving behind microscopic particles of iron and silicon. Around these celestial seeds, traces of water vapor freeze into crystals of ice just tens of nanometers across, finer than almost anything else in the sky. To see noctilucent clouds is to see a meeting of worlds: water from Earth, dust from space, sunlight from a sun already set, all woven together at the threshold of the void. Below them lie the more familiar clouds of our weather. Above them lies the thin edge of space itself, where the atmosphere fades into nothing. Researchers have observed that noctilucent clouds appear to be growing more frequent and more widespread in recent decades, and some believe this may be a quiet signal of changes occurring in the upper atmosphere, a whisper from a region we rarely think about, reminding us that the sky extends far, far beyond the reach of rain. Come back now, gently, to the more familiar sky, and let us think about color. For clouds, though we often speak of them as white or grey, are in truth painters of the most delicate palette imaginable. A cloud appears white because its droplets scatter all the wavelengths of sunlight equally, sending the full spectrum back to our eyes as a single pale brightness. But when a cloud grows thick, when its droplets crowd together and light must pass through layer after layer of water before reaching us, less of that light escapes and the cloud appears grey, then charcoal, then almost black along its underside. This is why a storm cloud looms so heavy against the horizon. Not because it has changed colour, but because its vast interior has begun to swallow the sun. And yet, at the edges of day, clouds become something else entirely. At sunrise and sunset, sunlight travels a long slanting path through the atmosphere, and along the way, the shorter blue wavelengths scatter away, leaving behind the longer wavelengths, the golds, the oranges, the deep reds, the soft magentas. These remaining colours strike the undersides of clouds and paint them in hues so tender that poets across every civilization have paused to describe them. In rare conditions, clouds can even shimmer with iridescence, displaying pale bands of pink, green, and lavender when their droplets are unusually uniform in size. Higher still, thin ice crystal clouds can produce halos, sundogs, and circumzenithal arcs, bright rainbow smiles suspended upside down in the sky, formed as sunlight refracts through millions of tiny hexagonal ice prisms, drifting in perfect alignment. Every color you have ever seen in a cloud is in some sense a conversation between water and light. The cloud does not manufacture these colors. It reveals them, acting as a slow, patient lens that sorts sunlight into its hidden components. And so each cloudscape, each sunset, each fleeting moment of gold upon grey is a kind of quiet spectroscopy, the sky teaching us, if we are gentle enough to watch, what light is made of. Now, as our thoughts grow softer, and the sky continues its quiet work above us, let us consider how clouds speak to one another across the planet. For clouds are not solitary travelers. They are part of an immense interconnected system, a circulatory pattern that moves water and heat around the Earth in ways so vast that no single human lifetime could trace them entirely. Warm air rises at the equator, laden with moisture evaporated from tropical seas, and as it climbs, it cools, releasing its water as the towering cumulonimbus storms of the tropics. This rising air then spreads northward and southward at great altitude, eventually descending again around 30 degrees latitude, where it arrives dry and warm, creating many of the world's great deserts: the Sahara, the Arabian, the Australian outback. This enormous loop is called a Hadley cell, named after the English scientist George Hadley, who proposed its essential shape in 1735. Beyond the Hadley cells lie other circulation patterns, the ferrule cells and the polar cells, each one a slow-turning wheel of air that carries clouds, storms, and silence across the globe. Within these wheels, smaller patterns emerge: the trade winds that once carried sailing ships across oceans, the jet streams that guide storms across continents, the monsoons that arrive each year with the rhythm of breath itself. Clouds are the visible signatures of these invisible motions. When you look up and see a long line of clouds marching across the sky in the same direction, you are watching a river of air that may have begun its journey thousands of kilometers away, above an ocean you have never seen. When you see clouds spiral gently around a center, you are witnessing the rotation of the Earth itself, gently bending the air through what scientists call the Coriolis effect. And in this way, every cloud is a messenger, carrying within it the story of distant waters, distant winds, and the slow, patient turning of our world through the long, quiet hours of the night. Consider now the quiet mathematics of a single raindrop, and the long, patient journey it undertakes before it ever touches the Earth. Within a cloud, water does not simply fall the moment it appears. It begins as something almost unimaginably small, a droplet only a few microns across, so light that the gentlest updraft can carry it aloft for hours, even days. For a droplet to become rain, it must grow, and growth inside a cloud is a slow and delicate affair. In warmer clouds, droplets collide and merge, a process meteorologists call coalescence, each tiny collision adding mass until at last the droplet is heavy enough to begin its descent. In colder clouds, the process is stranger still. Ice crystals grow at the expense of surrounding water droplets, pulling moisture toward themselves in a quiet exchange known as the Bergeron process, named for the Swedish meteorologist Tor Bergeron, who described it in the early 20th century. And so, somewhere above you, in the hush of a cloud you cannot see, millions upon millions of these gentle exchanges are taking place, each droplet finding its siblings, each crystal slowly thickening, until gravity at last begins to win. When the raindrop finally falls, it does not fall as a teardrop, though we have drawn it that way for centuries. A falling raindrop is shaped more like a tiny hamburger bun, flattened on the bottom by the air it pushes through, its top rounded by surface tension. The largest raindrops, those approaching about 5 millimeters, become so unstable that they break apart mid-fall, scattering into smaller droplets, and beginning the journey again in miniature. And through it all, the rain is returning water that may have traveled across entire oceans, lifted from the warm surfaces of distant seas, carried on rivers of wind, condensed in the cold heights of a cloud, and now, at last, finding its way back down. Every raindrop that touches your window has taken a journey measured not in miles, but in patience. A quiet cycle, older than the mountains themselves. Now let us turn our thoughts to snow, that most silent of weathers, and to the cloud-born crystals that drift down through the cold air in numbers too vast to count. A snowflake begins, as rain does, with a single speck, a microscopic particle of dust or pollen, or even a fragment of sea salt carried high into the atmosphere. Around this tiny nucleus, water vapor does not condense into liquid, but transitions directly into ice, skipping the liquid state entirely in a process called deposition. And here, in the freezing heights of a winter cloud, the crystal begins to grow, not randomly, but according to the quiet geometry of water itself. Water molecules, when they freeze, prefer to bond at angles of 60 and 120 degrees, And so every snowflake, without exception, grows with six-fold symmetry. 6 arms, 6 sides, 6 gentle branches reaching outward into the cold. The particular shape each snowflake takes depends on the temperature and humidity it encounters as it drifts downward. At around -2 degrees Celsius, snowflakes tend to form thin plates. A little colder, and they become slender needles. Colder still, and the familiar 6-armed dendrites emerge, those lacy, fern-like stars that have become the very symbol of winter. Because each snowflake falls through a slightly different path, through slightly different temperatures and humidities, each one ends up with a slightly different history written into its arms. It is often said that no 2 snowflakes are alike, and while this cannot truly be proven, it is very nearly certain. The number of possible arrangements is so astronomically vast that the odds of 2 identical flakes ever forming are vanishingly small. Consider for a moment what this means. Every snowfall you have ever witnessed, every quiet morning when the world was hushed beneath a blanket of white, contained trillions of tiny, unrepeatable architectures, each one a small and perfect record of its own descent, each one melting away within moments of arrival, its brief and intricate story dissolving quietly back into water. And so, for tonight, we pause here, somewhere between the warm, low mists and the high, cold ribbons of ice. We have learned that clouds are gatherings of invisible water made visible, that each droplet forms on a tiny speck of dust, and that the entire sky is organized into quiet layers, each with its own temperature and light. We have met Luke Howard, who gave the sky its grammar, and we have watched the cumulus rise from warm fields on a summer afternoon. There will be more to discover: the long-feathered cirrus, the storm-bearing cumulonimbus, the rare and strange clouds that glow at night. But none of that is needed now. Let the names soften, let the layers blur. Somewhere above the roof that shelters you, real clouds are drifting in their slow, unhurried way, shaped by the same physics we have traced tonight. Breathe gently, let your thoughts rise, cool, and dissolve, like vapor returning quietly to the sky. If you would like to drift further into the sky on future nights, you are welcome to stay with us. Tomorrow we will explore the storm clouds, the glowing clouds of twilight, and the rare skies that most people never notice. Thank you for spending your night with Let's Learn While You Sleep. Subscribe and come back tomorrow night. We'll be here. Sleep well.